Good afternoon, everybody. Thank you for being here. My name is Chahboub Yassine. I'm a PhD student at the University of Miskolc in Hungary. I'm very happy today to give a small presentation about my work entitled Damage Prediction of Ferritic Pipeline using Artificial Neural Network. So before going into the calculation and the simulation, let me just briefly introduce what I'm going to talk today. I will start by a general introduction, then I'm going to explain briefly the process, then results and interpretation, then I'm going to conclude by conclusion and perspectives. But before going into the details of the presentation, I would like just to ask you if you could remember these two numbers, because they are very important. So at the end you will understand why they are very important. So we have 6 hours and 30 days. As you know, when we are talking about the nuclear field, as researchers, engineers, and scientists, our purpose is that all the parts that are used in the nuclear power plants are working properly. One of these parts are the pipeline. So our purpose is how we can avoid the catastrophes, how we can predict the initiation and the propagation of the cracks, which means that we can avoid the consequences of the leakage problems. Unfortunately, I guess all of you know that there is no material which is perfect, which means that the cracks are present everywhere. Our purpose is how we can detect the presence of this crack, how we can avoid the problems of the leakage, which means how we can predict the crack, how it will propagate in the material. Then we will be able to avoid such kind of problems. Well, you may know that in order to make some mechanical tests for huge components, such as pipeline, we need millions of euros, so it's a lot of money. So our goal is how we can also predict the failure of the huge components in the cheapest way and in accurate, and we should find accurate and correct results. So maybe luckily we have many scientists that they did a lot of work in the last century, and they could develop an approach which is called global approach. And this approach can, we are going to face some transferability issue, but we can use this model to predict the failure of huge components, for example, the pipeline, based on small-scale specimen, as you can see in the slide. So, for example, based on the CT, cent, or not standard specimen, we can predict the failure of the pipeline. I'm going to explain later how, but this is the main purpose. So, as I told you, for example, there's Mr. Rosselier, he made his own model. Then Gerzel also made his own model, which is after that became developed by two scientists, Mr. Trigger and Netherlands in 1986. Then after that we have in the last 10 years, Mr. Zink, who made the complete GTN model. But today I'm going to talk about the GTN model. So I'm going to give you a small introduction about the model. So as you know, we have 3 steps of the ductile failure. So basically in 1975, Mr. Gerson developed the model, but he didn't take into consideration the last step of the ductile failure, the micro-void coalescence. So in 1986, Mr. Tvega and Mr. Nettelman, they could include in the model the micro-void coalescence, which means that the GTN model could cover the 3 steps of the ductile failure. And they could develop the GTN model. And as I told you, in the last 10 years, Mr. Zinn could develop the complete GTN model by introducing other parameters. So I'm not going to use the complete model. I'm just going to base on this on the GTN model that was developed in 1986. Okay, so here is the point. So the main purpose by using GTN model is how we can determine those H parameters. So it is really important to find a correct way to determine the H parameters, that they should have a physical meaning. So we are not choosing the parameters arbitrarily from our mind. We should have the parameters that they could help us to study the crack, how it will be propagated into the material. Basically, there was many studies which were based on the GTM model, and they could find that the values of Q1 and Q2 that are shown in this slide are almost fixed. So I will show you in a table some previous studies that was done in this field, and you will find that Q1 and Q2 are almost fixed. And my purpose now that I will focus how I could determine those 6 GTN of parameters. Okay, so there is one basic method. Is where we have to do many simulations and we have to find the correct set of parameters, then the simulation could fit the experiments. But it's time consuming. We need a lot of time to make many simulations to find one set of parameters, which take a lot of time. But lately, there was many methods that are trying to optimize the time consumed in the determination of the GTN parameters. For example, the HPSO and the artificial neural network, which will be my work today. The HPSO is a hybrid swarm optimization method, if someone is interested to know the abbreviation. Okay, so here is the methodology. So first of all, we should have, as you know, each neural network should have a database. So I used a not standard specimen as my database. So because, first of all, for a simple reason, because each simulation took for me just 5 minutes, so I don't need to do a lot of, I can do as much as I want of the simulation, and it won't take me a lot of time. Then I have to do the NT simulation for my pipeline. Then I should ask my neural network to predict for me the GTN parameters based on the experimental data of the pipeline. I will have more slides which explain this process into a simple way. Okay, so this is the Chahboub that I talked about. As I told you, like there was many studies that shows that the values of Q1 and Q2 are almost fixed. So Q1 is 1.5 and Q2 is 1. So I'm not going to disturb myself talking about determining these two parameters. I'm going to focus about the rest of the parameters. Maybe you can notice that the parameters are defined according to the type of the material, to the environment, to the temperature. So there's many parameters that could influence my parameters, and it's really hard to find them in the easy way. So here is just another slide to give you a simple way how my work will be. So I want to start from the notch tensile test, which is few centimeters, and I would like to predict the loads that could lead to the failure of my pipeline, which is like in meters. So this is like in simple way what is the purpose of my work. So I would like just to highlight here, I try to use as I told you, in order to find the GTM parameters in the, let's say the standard way, I have to make many simulations to find one set of GTM parameters. And for me, for the pipeline, I had to do 15 simulations. And each simulation, it took me between 2 to 3 days for one simulation. And like around 30 days, I could find my GTN parameters for this pipeline. So it's a huge amount of time. So you can imagine if I have 5 pipelines or even more, it will take for me months to determine the set of GTN parameters. So as you can see here, it's like the difference between the experimental and my simulation. So after finding my GTM parameters, I could make one simulation it is in gray color, and I could predict the failure of the pipeline based on GTN model. But it took for me, as I told you, 1 month, so it's a lot of time. That's why I decided to introduce artificial neural network. So what I told you first, that I have to provide my database for my neural network. So I have done 60 simulations, and each simulation took for me like 5 minutes, so it's like 300 minutes, which means 6 hours. Then with the 60 simulation, I could provide my data for my neural network. Then I trained my neural network by using MATLAB. And here is the main part. So after training my neural network, I used the backpropagation process, which means that I give the experimental data of the pipeline to my neural network, and I told him, please try to predict for me the GTM parameters for this experimental data based on the training that I gave you. So he was trained, he is ready to predict the GTM parameters. So back propagation, he goes from the experimental data and he goes back to determine the GTM parameters based on the pipeline. Then the last step will be to do one simulation to see if the GTM parameters that I found could predict the failure or not, which is the purpose. So this is just the set that I found. As I told you, the first values are almost fixed. So by using my trained neural network, I could determine the other 6 parameters. And now the main important step is to try these parameters and to see if I could predict the failure, if the experimental will be similar to the simulation or not. Okay, and here is the results that I found. In the curve in red is the results that were found by using the artificial neural network, and the black curve is for the experimental data. Maybe you can find a difference at the end. So in the beginning it was like literally the same, but at the end you can notice that they are not fitting each other. I have made some calculation and I found that could be basically due to the database of the artificial neural network. So I guess in the near future I will increase the data from 60 to 120 or 200, and to see if this curve could be modified or not. But basically the important thing that my neural network was a great tool, because in order to spend 30 days, I just spent 6 hours and they could find the set of GTM parameters that I was looking for. So this is just small conclusions that our GTM model was a great tool. So I didn't prove it myself, but it was proved by the other scientists. But I just confirmed that this GTM model is a great image tool that we can use in our work. And artificial neural network for me was a magic tool to optimize the time from my case from 30 days to 6 hours. And I can imagine with more development we can optimize the more and more the time. So my next steps, I'm going to increase the database to train my neural network. And in the next future, I'm currently working on the subsized specimen to see how we can use the subsized specimen in order to see to predict the failure of the pipeline, basically, and we will try to find some solutions for the transferability issues that we are going to face. Yeah, and that's all for today. Thank you so much.
Thank you. We have time for a couple of questions. I will have a couple myself. Hopefully someone else as well. Otherwise, maybe I can ask you a couple of them. So I'm a bit confused when you show the results. So the idea is to predict the failure.
Yeah.
But you don't show the failure, right? Because there's no drop in the load.
So my idea is to find the maximum load of the pipeline that could lead to the failure.
But if you go back to the results, so yeah, this is the failure point, and the fitting of this critical coalescence volume fraction will give you that failure. So a drop in the load current capacity that you don't see here.
Yeah. So here that was one of the main issues, because that was also lead to the database. So that's why I decided to increase the database that was used in the artificial neural network. Then my simulation could go until the failure. And
but in the final document also you didn't go down. I was wondering why was this the case. Was there like a convergence problem? Or?
So now here, for example, here it was like, it was the experimental data was provided by the loading and loading, as you know. And after that, my purpose, or the main purpose for me, is to find the maximum load that could lead to the failure of the material. Yeah, maybe I didn't reach the failure point because of the convergence problem in my software that I was using. So that's why I didn't reach the last point. It's a problem that I was facing from my first simulations, but you were right. Also, I faced some problem to reach the end of the simulation.
Yeah, that's not a challenging simulation. And I was wondering, so the plenary speaker tomorrow, one of the plenary speakers, Mehar Kuna, he has done quite a lot of work on artificial networks using to predict Gaussian parameters, so the same kind of ideas in the 90s. So I was wondering if you're using a different kind of neural network. I haven't really experience.
Yeah, for me, I used the back propagation concept, so I don't know if he was using the same, but for me, I read many articles and I didn't find someone who was like based on the. So for me, the main purpose is I was using the notch tensile specimen to predict the failure of to predict the loads and to predict the curve. So I didn't find such similar work that was based on the notch tensile specimen. And yeah, there was works based on the back propagation concept, but to use small scale, to use notch specimen, I didn't find some similar work.
Okay, thank you. Thanks.